Welcome back to chapter 2. Today we're going to talk about organizing and visualizing variables. This chapter is going to be very important for the project, which is part of this class. So make sure that you follow along. And if you have any questions, let me know. But again, organizing and visualizing variables is going to be crucial in order to get a good grade on your project. So today we're going to talk about how to organize and visualize categorical variables and numerical variables. So there are two different ways to do that data based whether it's categorical or numerical. We will talk about how to summarize a mix of variables. So there's going to be a situation where you're going to have more than one variable. You're going to have a mix of those. So we'll talk about how to summarize those as well. And then finally, we're going to talk about how to avoid making common errors when organizing and visualizing variables. So you definitely want to keep that in mind as you work on your project. Remember we did talk about the DCOVA at the beginning of the semester. So one thing that you need to keep in mind is when organizing data, the organization and the visualization usually is just one step. Kind of you combine those because it kind of happens at the same time on the DCOVA method that we're going to be using. So remember, categorical data is data that you can break them into categories, right? So if you have a survey asking people, do you use Facebook? Yes or no? So category yes, category no, maybe a third category that says maybe. But so when you have categorical data like that, you want to use the tallying data. And then you can have one variable. If that's the case, you want to use a summary table. If you have two or more categorical variables, then you want to use a contingency table. Here is a summary table, really simple, right? You did a survey and you asked millennials what type of devices they use to watch movies or television sets. And you collected your data, you break it down into percentage, and then you put it in there. Just by looking at this, you can tell that the number one device that millennials use for watching TVs and movies is a television set with 49%. So that is your summary table right there. Again, you will need this for your project. So make sure that you know how to summarize data. Contingency table also help you organize two or more categorical variables. So sometimes you're going to have more than just one category. And in that case, you might have to use a contingency table. And it's used to study patterns that may exist between the responses of two or more categorical variables. You can also use this to cross-tabulate or tally jointly the responses of the categorical variables, or you can use that for two variables. The tallies for one variables are located in the rows, and the tallies for the second variables are located in the columns. Let's watch an example. Here it is, right? So basically, this company is trying to find out if there are errors on their invoices, and they break it down based on how much the invoices are. So they have the small amount, the medium amount, the large amount. And really simple here is your contingency table. On the first column, you have the categories, small, medium, large. And then you have whether they have no errors, and then finally you have your totals. Here is pretty much the same data, except that you are putting them into percentages. So putting it into percentages kind of gives you a better idea right off the back. So we know, for example, just looking at the first table, we know that most of the errors are coming from the medium amount invoices, 40 of them. But once you put them into percentages, you know that it's 10% of the errors are coming from the medium amount. How to calculate the percentage? You guys should already know that. Fairly simple, right? You grab your total. In this case, let's grab the first amount, which is 170, and then you divide it by the total number of invoices that you have. That is 400, and that's how you get your total amount, 42.50. That you can say 42.50 of the invoices are from small amounts and they contain no errors. And you can say 5% of the invoices have errors are from the small amount. Here we have the same data, but we have percentages based on the totals of the amounts. So once again, on this case, you're grabbing the 170 invoices that have no errors from the small amount, and then you divide it by the total amount of a small amount invoices, which is 190. And you can say, well, out of the small amount invoices, 89.47% of them contain no errors, and 10.53% contain errors. And then on the third column, you get your totals for the small amounts, which are at no errors plus errors. On this one here, we're presenting the same data, except that on this case, we are looking at the percentage of errors. So the first column tells you that 50.75% of all the invoices that have no errors are from the small amounts. And if you look at something that we noticed right from the beginning, is that the median amount of invoices contain the largest amount of errors. In this case, we can say out of the total errors on the invoices, on the 400 invoices that we picked, 61.54 of all the total errors are coming from the median amount. Okay, so when it comes to numerical data, we can use tables to organize the numerical data. And we can use the order array, we can use the frequency distribution, and we can use cumulative distribution, or we can use all three of them, and we'll see how. So what is an order array to begin with? It's really simple. You grab your data, and then you rank them in order. And normally you do from minimum to the maximum, or from the largest to the smallest, depending what you're trying to achieve. You're going to use the range. With the range is basically grabbing the highest value that you have available, subtracting the lowest value that you have available, and that is your range. Yeah, the good thing about this, it can help you identify outliers. So on this data here, we have the age of college students. So if you, for example, you say you have a 14-year-old, that will be an outlier because most 14-year-olds are not in college. Or if you have a 65-year-old, that will also be an outlier. Most people under 60s, they're not in college, they're not college students. So you could have those outliers. By doing the order array, you can quickly identify when you have those outliers. So again, the frequency distribution basically is just a summary table in which the data are arranged into numerical order classes. And so basically you grab your data and then you break it down into different classes. You have to do the class grouping for the table, and you determine how big you want those groups, those classes to be. So basically, what is appropriate amount of division between those groups. And normally you want to do at least 5, because if you do less than 5, it's really not useful. But you don't want to do more than 15, because once you do go over 15, then it becomes too bothersome. It's really losing also the value of what you're trying to achieve. To figure out how big or the width of the class interval, what you want to do is you want to divide the range by the number of classes that you want. So let's look at an example. Here is our data, right? And on this example, somebody is trying to, is collecting the temperature for 20 days that are happening during the winter. And here is our data. First thing we do is we sort the data in ascending order. So our lowest day is 12, and the temperature for the highest data was 58. In this case, we find a range first, which is 58, right? Highest value, minus 12, the lowest value, that gives us 46. Really simple. We want to use 5 classes, right? Because there is not a whole lot of data, so 5 is good. So what we do is we divide, we got 58 minus 12, that gives us 46. and we divide that by 5, and then that becomes around, what, 9.1, something like that, and we round up. So we do 10. So in this case, the class interval is going to be 10, and then we put our boundary limits based on that 10. So for the first class, we have 10, but less than 20. So we want to get the days where the temperature is at least 10 degrees, but more than 20. And on the second class, we do 20, but less than 30, and so on and so forth. You also want to get your class midpoints, which is fairly simple. You add the lower boundary plus the higher boundary, and then you divide by 2. So the first one is 10 plus 20, that gives us 30, divided by 2 gives us 15. So your class midpoint is 15. For the last one is 50 plus 60, that gives us 110, divided by 2, that comes to 55. And then what you do after that, you count the observations and you assign to classes. And here it is. So we have our ordered array starting from 12, which is the lowest, to 58, which is the highest. And then we count the frequencies for each class. So we have our midpoints, right? 10 plus 20 divided by is 30, divided by 2 gives us 15, and that's our midpoints right there. And then we count our frequencies. So let's count the first one, right? We have 12, 13, and 17. So we have 3. Our frequency for the first one will be 3. The second one says 20, but less than 30. So we have 1, 2, 3, 4, 5, 6. And that's our frequency. One thing that you need to keep in mind is when you do your totals, you have to make sure that the total equals the same number that you have for observations. So you know, we already talked about that we have 20. In this case, our frequency, we can see our total is 20. If the number was 19 or 21, that would tell us that either we missed one or we added one. So that's a quick, easy check that you can do to make sure that you collected all the data. On this one here, we can do percentages, which is a lot easier to give us a better picture. So we know we have 3, right? The frequency for the 10 but less than 20 is 3. We already know that. But putting that into percentages, it gives us a better perspective. So we know that 15 divided by 3 divided by 20 multiplied by 100, that'll give us 15%. So that is our percentages, 15%, which is the relative frequency is 0.15. One thing another easy quick check here is you want to make sure that your percentage equals to 100%. So once you add all of those, it should equal to 1%, 100%, and your relative frequency should equal to 1. Okay, on this one here, we have cumulative frequency. And this is convenient because it gives us a better view, better idea of what we're trying to achieve. So taking a look at the first one, right? So the first class says 10 but less than 20, so we know we have 3, which should give us a 15%. The second one, we have 6 days where the temperature was at least 20, but no more than 30, right? 30 or less. And that was 30%. So what we do, we add 3 plus 6, and that'll give us 9. And we add 15 plus 30, that'll give us 45. For the next one, we have 5 observations. So when we add 5 plus 9, that gives us 14. And 45% plus 25%, that gives us 70%, which is our cumulative percentage. This is convenient because by just looking at this, I can tell you, you know what, 70% of all the days that we recorded, the temperature was less than 40%. So it's very easy, very convenient to do the cumulative percentages. One easy check on this is, again, checking the totals. This one right here should equal 100%. So that means you're not missing anything. And your cumulative frequency, once again, it should also equal the numbers of observations. So that's just an easy check to make sure you did not miss any data. Why you want to use frequency distribution? Very easy. It puts all the data, all the raw data into a useful form. People can just look at it and don't have to analyze this data. They're already, wow, yeah, you know what? That's convenient. We had a cold winter because 70% of the days were below 40 degrees. Also, it allows for a quick visual interpretation of the data. And finally, it enables the determination of the major characteristic of the data, included where the data are concentrated in clusters, so you can see where most of your data is coming from. Those are the advantages of using frequency distribution. Some tips that you need to keep in mind when using frequency distribution is that different class boundaries may provide different pictures for the same data. So you have to be careful when you put those boundaries. You want to do everything, 10 and 30, 30, right? So more than 10 but less than 30, and then more than 30 but less than 60. So you have to keep in mind of those, because if you change those class boundaries, you can change the picture of what you're trying to achieve. Also, shifting data concentration may show up when different class boundaries are chosen. So you kind of had an idea, oh, you know what? Most of the days were between, uh, 30 and 40 degrees, but all of a sudden you change your boundaries, the data might look a little bit different. So that's something you need to keep in mind there. And also the size of the data set increases. The impact of alterations in the selection of class boundaries is greatly reduced, so you have to keep an eye on that. And finally, when comparing two or more groups with different sample sizes, you must use either a relative frequency or a percentage distribution. So keep that in mind. It's very convenient to remember that. Okay, now let's talk about visualizing categorical data through graphical displays. So this also is going to be a big part of your project. You want to keep an eye on this and make sure that you follow some of the things that we're going to discuss here. So you have your categorical data, right? Quick, simple question. You use Facebook? Yes, no. And then, so it's a category, right? Yes or no. So you want to visualize the data. So for one variable, you have your summary table, and then you can use a bar chart, you can use a Pareto chart, or you can use a pie or donut chart to visualize this data. If you have more than two or more variables, then you want to use a contingency table, and in those cases, you want to do a side-by-side bar chart, or you want to use a donut chart. So here is the bar chart. I personally like the bar chart being on a vertical position. In this case, it's on a horizontal position, which is okay. But I personally, I prefer those bar charts to be horizontal, to be vertical and not horizontal. So going back to the first question that we asked, is the television set. We already knew that was 49%. So you guys can see here the bar chart is the longest one because that's where most of the data is coming from. Also, one thing that is important here on the bar chart is that there is a gap between each data. So they're not next to each other, but you have that gap. Another way to visualize data is the pie chart. So the pie chart basically is just a circle, and then is divided into percentages or into the data that you have. As you guys can see, almost half of the pie chart is yellow, which represents the television set, or the 49%. Something similar to the pie chart is the donut chart. The donut chart is kind of like a pie chart, except that it has a hole in the middle. So that's where it gets its name. And the other pieces represent the data. So the Pareto chart, in the late 1800s, early 1900s, this very smart person called Wilfredo Pareto did some study, and he realized that 20% of all the people living in Italy own 80% of all the wealth in Italy. And the more he studied, the more he realized that that is very similar to other things too. So then he came out with the Pareto law, basically saying that 80% of all the effects that we have is caused by 20% of the causes. So That's why they, do a lot of things. You see, well, at your house, you use 20% of your utensil to do 80% of the cooking, and uh, and that's where you got that 80-20 rule. It comes from Wilfredo Pareto. Anyway, so the Pareto chart can help you uh, put that into perspective and is used to portray categorical data. And basically, it's just a vertical bar chart where categories are shown in descending order of frequency. And then you have the cumulative polygon is shown in the same graph and used to separate the vital few from the trivial many. So that's basically trying to represent that 20% of the causes causing 80% of the effect. So here we are, here we have some data, and so this bank is trying to figure out why there are some ATM transactions that were not completed, and they have different categories, right? So maybe the card was warped, was unreadable, maybe there was some issues with the ATM, or the ATM didn't have cash, so on and so forth. So you have your frequency, how many of the observations are coming from each category. Then you break those into percentages, and then you do your cumulative percent. So we already did that earlier, and we put that into the Pareto chart. And here is the Pareto chart. So here we can see here most of the observations are coming from the warp card. And then right over here, we can see how the 80-20 rule, that's what this is supposed to do, because we are doing the cumulative here. So that's what all the Pareto chart is, having this bar graph at the bottom. Just remember these are going to be vertical and not horizontal, and then you have this other graph at the top, which is the accumulative of all the observations. Okay, side-by-side chart basically is data from the contingency table. So here is our contingency table. Remember how we were studying those invoices, and so here we have the orange, the yellow represents the errors, and the green on this case represents in this one we have invoices size split out by errors and no errors. So here we have the errors and we have no errors. So invoices with errors are much more likely to be of medium size. We already knew that because we already seen the data, but putting it in a visual way, we can see where that is coming from. So the yellow ones are large, and the white ones are large, which you can barely see here. That's what the problem is. We can see the whites are large. We can see the yellow are the medium invoices, and the green are the small invoices. So this puts the data that we have here into an easy way to see that. Here we have a donut chart. This one can be used to represent data from a contingency table. Once again, here we have the same data and that we had it on that one. We just put them on the donut chart. And again, the white ones are the large, the yellow are the medium, and the green ones are the small. Let's discuss how will you use visualized data, numerical data, by using graphical displays. So you have your numerical data, right? And then remember how we did the order array, and then we're going to talk about the stand and leaf display. And then you have your frequency distributions and your cumulative distribution, and you can use histograms, Polygon, or the Ogive for the visualize the data. So what is the stand and leaf display? Basically, the stand and leaf is just an easy way to put data and distribute it where the constant, so you can see where most of your data is coming from. And it's really simple. You sort the data into leading digits, that's what you call the stems, and then you have the trailing digits, that's what we call the leaves. Okay, so remember how we have that age of the students here. So on this case, our stem is going to be the 10 or the 1, right? So the decimals is going to be the 1, on this case 2 decimal, which is 20, and so on and so forth. And then the leaf is just the second part. So you grab the 1, and then you grab the 6, and that goes in here, and then you don't have to repeat the 1. That's why it's called the stem, because the 1 stays there. So we know the first number is 16, the second one 17, the last one here is 19, the one before that is 19. This one will be 20, another 20, 21, 22, the last one here is 27, and then we have on the 32 and 38, and finally we have 42. So stem basically will be the decimals, and the other numbers you just add them on as the leaf, and those are the single numbers. One thing that you can use to visualize this numerical data is the histogram, which is kind of like a bar chart, or is a bar chart, but the difference is there are no gaps in between the bars. So we call that a histogram. And on this case, the class boundaries or class midpoints are shown on the horizontal axis, and the vertical axis is the frequency or the relative frequency or the percentage, whichever way you're presenting it. And finally, the height of the bar represents the frequency, relative frequency, or percentage. So here, this is what it looks like. Here is a histogram. As you can see, the difference between a histogram and a bar chart. One, the histograms are always vertical, so they're not horizontal, and there are no gaps between the data. And how high they are just represent the frequency. So just looking at this at the first class, we can see that is 50% of the data, and we can see that right there. So one thing that you need to keep in mind is here in the histogram, the vertical axis will be defined to show the percentage of observation of classes, right? So here it is, right? Remember the midpoint that we find, the 5, 15, so on and so forth. Okay, another method to visualize data is the percentage polygon. So percentage polygon basically is just formed by having the midpoint of each class. Remember how we find those midpoints? So you have this midpoint, and then you represent the data in the class and connect the sequences of midpoints are the respective class percentages. The cumulative percentage polygon, or Ogive, displays the variable of interest along the x-axis and the cumulative percentage along the y-axis. And this one can be very convenient when you have 2 or more groups to compare. So here it is. This is the frequency polygon. Again, you find your midpoints, and then you just connect the dots. Really simple. Here we have the percentage polygons for 3-year return percentage for the growth of value funds. So once again, here is the growth represented by the blue line, and the orange line represents the values. Here is the, again, this is used when you're comparing 2 or more groups. So you have, on this case, you were comparing the restaurants for the center of the city or for the metro area, and you have the cumulative data here, and then you just connect with the dots. That is fairly simple. On this one here, we're looking at the cumulative percentage polygon, which is the cumulative percentage polygon for the 3-year return percentage of the growth and value funds. It's kind of the same thing, you just got the return percentages here. Let's discuss visualizing 2 numerical variables by using graphical displays. So remember, you have 2 numerical variables. You can use the scatter plot, or you can use the time series plot. What is a scatter plot? Basically, their use for numerical data consists of pair observations taken from two numerical variables. One variables are displayed on the horizontal or the x-axis, and the other one is displayed on the vertical or the y-axis. Scatter plots are used to examine possible relationship between two numerical variables. So let's look at an example to make sure that we got this. So we are the volume per day and the cost per day for this data here. And then you can see here you have the first point is 23, right? The volume per day is 23. So the cost per day is 125. And so you put your point there between 23 and 125. The last one, the volume per day is 60, and the cost per day is 200. So you have 60 and 200, and then that's how you get your scatter plot, by putting the data where those 2 points meet. So once again, one is on the y-axis, the other one is on the x-axis, and you find your data, and then you put your point there. What about the time series plot? So the time series plot is also used to study patterns in the values of a numerical variable over time. And numerical variables values go on the vertical axis while the time period is on the horizontal axis. So what does that mean? Here it is, right? So in this case, you want to calculate the number of franchises this company had. So you can see in 2009 they have 43, in 2017 they have 95. So what you do is you're going to put your years here on the x-axis, and you're going to put the number of franchises on the y-axis here. So you grab the first one, 2009, and then you look at it where 2009, and then in 43 meets, and that's where you put the dot. And basically it's kind of like a scatter plot, but you use the dates, like years, months, or whatever dates you need for the time series. Okay, organizing a mix of variables. So what happens when you have different variables? You might want to use a multidimensional contingency table. A multidimensional contingency table basically is constructed by tallying the responses of 3 or more categorical variables, and can be used to discover possible patterns of relationship that may have between all those multidimensional data. The simpler the tables and charts, the easier charts will fail to make apparent. So that's something you need to keep in mind. As a rule, you want to make sure that the tables be limited to no more than 3 or 4 variables. If you go more than that, it's not as useful. In typical use, these tables extend contingency tables to 2 or more row of column variables, or replace the frequency found in a contingency table with a summary information about a numerical variable. And here is an example, right? So on this one, you have 2-dimensional tables showing font type and risk level for samples of 479 retirement funds. So here you have your growth, you have your value, you have your grand totals, and then you have your risk level from low to average, high. And on the 3-dimensional table here, we have the type, the market cap, and risk level for the sample of 479 retirement funds. So you have all of those. So again, you want to keep this to no more than 4, because once you go over 4, then it could be too much data and it could be convoluted, and it loses the value that you're trying to present. In Excel, you can create pivot tables, and they're very convenient to use. You can manufacture them to represent the data that you're trying to do. Basically, you put all your data into Excel, and then you insert a pivot table, and that will help you display the data. In the jump, you can also create a table that is interactive. In Minitab, you can create a table, but it's not really interactive. So Minitab is not as strong as Excel or the jump for this. And finally, jump and Minitab have many specialized statistical and graphical procedures. you can use to analyze and visualize multidimensional data. You can do the drill down in a table to reveal data in the table summaries. So in Excel, if you click on a cell, you can use the table display rows and data associated with a cell. In Jump, you can click on that cell and it will highlight those rows of data that are the source of the cell. And the drill down is perhaps the simplest form of data discovery. So basically you click on it and you can drill down and it'll give you the data. So here is an example, right? So this is from Excel. If you click on the 6.61, then it opens the data telling you where the 6.61 is coming from. These plays to visualize a mix of many variables. Continuing with that, you have these plays that are more useful than multidimensional contingency table with many rows and column variables, and we'll see with that in just a minute. So the data, not just summary statistic, can be shown for numerical variables, and multi-numerical variables can be represented in one summarization. And finally, visualizations can repeat patterns that can be hard to see in tables. So this is what we mean here. We have a color scatter plot. We visualize both numerical variables and categorical variables. So on this case, the red represents large market capitalization funds. And one, they can be relatively have best return and lowest expense ratios. And two, some have either low returns or high expense ratios or both. So here is the Jump color scatter plot. You have your expense ratios on the y-axis, and you have your 3-year return on the x-axis, and then you can see the different colors represent the different market caps. Bubble charts, extended scatter plots, basically this is the use of the size of points called bubbles to represent the value of an additional variable. In Excel and Minitab, the additional variables must be numerical. In Jump, the variable can be either numerical or categorical. That's something that will be represented there. Here is a pivot chart, which visualizes specific categories from a pivotable table summary. And basically, here we have your pivot chart in here that we already created. And then you have your data here summarizing all that data from Excel. In this case, we're looking at low risk, small cap, market cap, and we have funds that have the highest mean return among low risk funds. Treemaps are graphical displays of contingency table. Here we can see on the left, we can see an Excel treemap, and basically the size of titles corresponds to the frequency in a cell. So the more frequency you have for that particular cell, the bigger it's going to be. And so you can see here you have your growth, which is large, mid cap, small, and you can see which one is the bigger. On the Jump treemap, the sizes of titles corresponds to the value of the numerical variable from the market cap. So, basically the bigger it is, the more data that you have there. Sparklines are compact time series visualization of numerical variables. So here you have movie revenues per year from 2005 to 2006. So you have that time series, and you see how that is going there. And then you have movie revenues by week per month, and then you have those time series here on that DCOVA. Filtering and querying data. So two operations associated with preparing tabular or visual summaries are data filtering and querying. And data filtering basically select rows of data that match criteria, and you have those specific values for specific variables. You have data querying is similar but may not select all of the columns of the matching rows. And Excel, Jump, and Minitab all have various filtering and query features. So let's take a quick look at those. Here is an example For the jumping Minitab filtering query, on this case, you want to filter it to the 10-year return, and you want to say it's greater or equal to 9, so you can filter it that way. In Excel, you can use the slicers, which are convenient because you can use the slicer to filter the data that you need. And basically, it's just a panel of clickable buttons. So you click on it, it expands and superimpose over a worksheet. Each button in slicers represents a unique value of a variable found in the source data or a pivot table. And by clicking buttons on the slicer panels, you query the data. So here is example. We see we have 4 slicers below. And then you can ask questions. So what are the attributes of the funds with the lowest expense ratio? What are the expense ratios associated with large market cap value that have a star rating of 5? So here we are. You have your growth, you have your average, your high, you have your totals, and then your slicers there. So here we are answering those questions. What are the attributes of the funds with the lowest expense ratio? And then you can see here 0.29, right? The updated pivot table, not shown below, reveals only one such fund, which is 0.29. And on the other one, what are the expense ratios associated with a large market cap value funds that have a star rating of 5? And here you are, you click on the 5, and then it opens the expense ratios, which is from 0.83 to 1.19. Some of the challenges that you're going to find when you're trying to organize your data or visualizing your data, you need to keep in mind is that not everybody thinks as you do. So you say, wow, this chart looks good, but some other people might not think that looks good. Like I said, I personally prefer those bar charts to be verticals, but some people might prefer it to be horizontal. So that's something you need to keep in mind, that other people have limited ability to perceive and comprehend. So you need to keep that in mind. Presentation issues that can undercut the usefulness of methods from this chapter. It is easy to create summaries that obscure the data or create false impressions or contain chart junk. That's something you need to keep in mind, especially for the project. You don't want to make sure that you don't have any chart junk in there. Here is an example of obscuring the data. So what does that mean, obscuring the data? Basically, even though you presented the data, you're making it look irrelevant or that is not meaningful. So here you have a side-by-side chart for retirement funds, and then you have your risk levels. Another thing that another mistake that you can do is have false impressions can be created by many ways. So you may create a false impression of your data. And one of those things that it can be done is by selective summarization. Basically, you're only presenting part of the data that you collected, so you are ignoring some of the data that could make a difference, and you are ignoring it because it doesn't represent your values. It doesn't represent what you're trying to achieve. You can also have improperly constructed charts, potential pie chart issues where it looks like it's bigger than it needs to be. You have improperly scaled axes. So in the scale, you make it big enough that when people look at the data, it doesn't look like it's a huge difference. But if you zoom in into it, you can actually see the difference. A y-axis that does not begin at the origin or is broken, so you're not getting all of the representation that you need because you are not starting at the origin. And you can have those chart junks. See, here is an example of selective summarization. In this case, you can see, for example, if you look at the column, it says change from prior year, right? Company A, 7.2%, that looks good. Company F, 35.1%, that looks really good. But you are ignoring the data for year 1 and year 2, which all of those are negative. So when you look at company F, for example, that you look really good at 35.1% from last year, but you're ignoring that on the year 2, it was negative 37.8%. So this is an example where you can not present a data that is important for somebody to say this is an investor. You're trying people to invest on these companies, and then you are not presenting the data from year one and year two because it affects your interest. Now take a look at this. How obvious is that both pie charts summarize the same data? It's kind of hard to tell, right? I mean, think about this. Look at this. It's the same data, but it's kind of hard to tell that it's the same data. Here is another graphical error. There are no relative bases, right? So a student receiving A's. So you have numbers there. You have your freshmen, you have your sophomore, you have your juniors, you have your seniors. So look at that. You have, that doesn't really tell you anything. But when you put it into percentages, you see how those columns changes. So the percentage of freshmen is about 20%. Well, here you can say, yeah, most of the people receiving 8 are freshmen because there are so much more freshmen than seniors, right? But when you put it into percentage, that'll give you a basis comparing those data. On this one here, you are compressing the vertical axis. So you can see here quarterly sales, right? You can see quarter one and quarter two is fairly similar, right? Quarter three was really good. Quarter four went down a little bit. But because you are compressing the data, you really cannot tell the difference. Once you decompress the data, then you can see how much difference between quarter one and quarter two, even though here they look somewhat similar. Even quarter four and quarter one, they look kind of similar. But once you decompress the data, you can see that quarter four is actually smaller than quarter one. The problem with this one is there is no 0 point on the vertical scale. So here you're just starting at 36. So even though it's the same data, you really cannot tell where the origin is. So when you want to do that, you gotta put the scribbly line in here, and that tells people that this is not up to scale. So it's not going from 0 to 36. The difference, the high from 0 to 36, it will not be the same between 36 and 72 because you don't really need that data. But by putting this line in here, you are letting people know that is the case. Chart junk. This is something, especially for the project that you want to avoid. Here it is, this person is trying to be very intuitive, trying to make this look, cute or whatever. But, so you have a tree here and, kind of representing the leaves. This is just bad representation, right? Instead, they can just use clear data so you can look at it. See here, you have your acres on the y-axis. You have your growing season here. So much easier to see than all of these cute little data on the left. So some of the best practices, some of the things you need to keep in mind when you're constructing visualization. Use the simplest possible visualization, just trying to be too cute, too much data, too much visualization could also impede or not present your data clearly. Make sure you always include a title and label on all axes. Very important, so you know what you're talking about. So if you're talking about dollars, make sure that people know what is dollar, which columns are. So make sure everything is labeled correctly. You gotta make sure you include a scale for each axis if the chart contains axes. Begin the scale for a vertical axis at 0 and use a constant scale. If you can't or you don't need to, make sure that you use the scribbling so people know that it's not up to scale. Avoid 3D or the export effects of especially the pie charts. Some people think the 3D looks pretty cool or the explorer looks pretty cool, but it loses the meaning of what it's trying to achieve. Okay, use consistent coloring in charts meant to compare. So, for example, if you're using green to represent freshmen, make sure that you use the same color throughout your presentation. So don't change the colors. That way people don't get confused. And finally, avoid using uncommon chart types, including radar, surfaces, bubble, cone. There are other charts in there that, you know, that are uncommon. People won't really know what to use. So try not to use those as much as you can. Okay, that will wrap it up for today. And so remember, we covered about organizing and visualizing categorical variables. We did talk about organizing and visualizing numerical variables. We discussed the summarizing of mixed variables and how to avoid common errors when you're trying to present your data. All right, if you have any questions, feel free to reach out.